Hello everyone and welcome back. So, today, there we go. We're going to be learning about linear impulse and momentum. What is that? Well, you'll find out. So where does this come into play? Well, things like this. You have a dent in a trailer fender perhaps, or in your car's bumper, and you want to get it removed. And what you'll use is an impulse tool. It looks something like this. You drill a small hole in the bottom of the top of your fender. And then you will bolt on this tool onto it. And then that has a slide hammer that you run and you just jam it upwards until it hits that stop ring. And it will slowly but surely pull it upwards. Now, why do you want to do this? Well, for various reasons. Maybe you can't get the tire out so you can smack from the other side. There's various reasons it might be better to do it this way. So this is an example of an impulse tool. A very large force over a small period of time moving something. So, things you might wonder is how can you figure out the amount of linear impulse? And could you look at a carpenter's nail and hammer the same way? The answer is sure. Okay, baseball, another example of this, or soccer, even football in a way. Because this bat is going to apply an impulse to that ball, possibly, or at least that catcher will be when he catches the ball. And so what's going to be happening is that impulse is going to change the velocity of the ball. And it does that by applying a force over a small period of time. So things we might wonder is impulse a vector? Is it pointing in the same direction? And could we figure out what the resultant motion of the ball will be if we knew how the bat was hitting the ball and for how long it was in contact? Finally, a third example would be like when you have a stake and you have a sledgehammer smacking it into the ground. And that sledgehammer applies a very large impulse to the stake, a very large impulse, which the ground is trying to resist. So if you know the initial speed of the sledgehammer and how long it stays in contact, even though that's a very small amount of time, it is finite. It does stay in contact there for a very small amount of time. Can you figure out how far it's going to push this into the ground? Well, the answer is yes. If you know how resistive the ground is to that. Okay, so we're going to be using this thing called the principle of linear impulse and momentum. It's a fairly simple equation, and we get it by integrating the equations of motion with respect to time. Now, this is usually useful for problems where we have force, velocity, and time. Also, going to understand how the mechanics of impact, which is going to be in a later section. That's where you have something collide, just two cars driving into each other. Brace for impact, that kind of thing. There's a wall. So, here's our original equation of motion. Now, you know acceleration is actually equal to the derivative of velocity with time, and that's how we can integrate this. So we're going to integrate both sides. Our mass is assumed to stay constant in this case. So that is not always the case. If you're doing like rocket propulsion, you have to take into account changes in mass as well. And what we'll get is the sum of all of our forces integrated with respect to time would be equal to my change in momentum. So this is my impulse right here, and the impulse applied will change my momentum. And this makes a lot of sense. If I have a catcher's mitt, and I am holding, trying to catch the ball, well, I apply a force to stop that ball. That ball's velocity goes from some finite value down to 0. And its momentum goes to 0. And so that's what's happening here. You are applying a force over a short period of time. Now, linear momentum is this vector mv. Mass is a scalar, so it's more like a scaling factor, but then multiplied by the velocity. It's often denoted as L for linear momentum. Now this always has the same direction as the velocity, never different. Linear impulse, linear momentum, linear impulse, is this integral right here, like I said last time. It's also a vector quantity, and it's always in the same direction as f. It's often denoted with an I. Now, it will go back and forth. You'll see it both ways, so please get used to that. Though I do honestly like this one better just because it's more clear. You can also figure this out by graphically looking at how the forces change with time. If it's some nice linear graph, well, then you can take the area of that pretty simply. Something that's a bit crazier, like this curvy line I have here, well, you have to do an integral. You can't escape it. But it's not too terrible. And right here, it's showing you how you can figure out the impulse if force is constant. Okay, so finally, putting all this together, we get our principle of linear impulse and momentum. It might remind you of similar equations we got in the past, where we had, let's see, T1 plus, V1 is equal to T2 or some sort, or T1 plus work is equal to T2. My initial kinetic energy plus some applied work is equal to my second kinetic energy. So same thing here. Initial linear velocity, some applied impulse gives me some final momentum. Sorry, I should have said momentum earlier. And we kind of see this in what might be, perhaps a ball being hit by a bat. The bat strikes it, the ball is now going into a different direction. It was this way, now it's this way. Okay, so the last thing we'll get into before we go into an example is the scalar equation. Since it's a vector equation, you can break it up into 3 scalar components. So which is nice, because that gives us more equations to work with. The x, the y, and the z. Do not forget this. So you take the sum of the integral of all your impulsive forces times time, plus the sum of all your impulsive forces in the y, and just keep them going down there, and you'll have 3 equations to solve for the 3 components of your velocity. So it can help us to apply linear momentum in a more complex system, which might be in the x, y, and z directions. Okay, yep. So we'll stop there for now. Next time we'll do an example, and we'll have some fun jumping into that. So thank you for listening. Remember, this is the equation that you need to memorize or write down. And I'll see you all next time. Have a wonderful day. Bye-bye.